Excellent. Thank you for that introduction and for the invitation. I'm interested to present this work, this research. And when I say research, I guess this will be a combination of research that our team has performed in the traditional sense where you do a project and then you go and test it and so forth and you get it published. But really, almost like the second half of this talk will be a different sort of research, the research where you get to really delve into other people's research. You get to read it, you get to go down rabbit holes and so forth. And certainly, it's been very interesting in terms of going from being an academic and not having much time to do that sort of stuff to having much more freedom to do it. So that's almost like one message. Hopefully, people get to understand that it's very important to read research. But really, I think what I'm trying to present today is almost like a chronological account of the way that I've learned about light and how it affects sleep and circadian rhythms and so forth, but with probably much more of a focus on this one in how it affects health. So really, to start at the beginning, this is basically a picture of my PhD not students, supervisors, Helen Wright, who's obviously there on the left, and Professor Leon Lack. And this is data from Helen's PhD. So she was pretty much at the tail end of her PhD while I was starting mine. We shared an office. And she was looking at basically what different wavelengths of light can affect the timing of the circadian rhythm, looking at the melatonin rhythm. It had been around this sort of time where certainly the discoveries were that short wavelength light, that is blue light, green light, were able to suppress melatonin. But this was really not just looking at the suppression of melatonin, but also really can it change the timing of the circadian rhythm? And the method to do this was to basically wear these LED glasses, which were in-house glasses, two LEDs per eye, connected to a battery pack. I was actually a participant in this study of Helen's. And the graph on the right was looking at the ability of different colors of light, different wavelengths of light in being able to delay the circadian rhythm. And so we had to basically sit in the dark for a period of time, maintain a fairly constant posture, chew on salivettes to sort of measure our melatonin throughout the night. And then from midnight until 2 a.m., that's when we had to put on these glasses. And so the graph on the right shows the different colors, so blue, blue-green, green, amber, red, and we also had a control condition that we underwent, which was also basically no light. It was sunglasses. And as you can see here, really, it was the short wavelength light. It was the blue, blue-green, and green that was the most potent at delaying the circadian rhythm relative to the control condition. Yellow didn't do anything, and red didn't really do anything. If anything, it trended in the other direction. And I think what's interesting about this is that these studies occurred around 2001, 2004. And it's really around that time when we had these discoveries and also in the 1990s, where really the short wavelength light, particularly blue light, was shown to suppress the circadian rhythm and so forth and increase alertness. And I think really the circadian field started to pay attention a lot to these short wavelengths of light. And what was interesting is that as much as this particular study was published in 2001, it took 11 years for this study to actually turn into a commercial device, which is very different these days. These days, you almost like see new products on the market and there's no science behind them. And just to catalog, so we've got the one that was tested in the upper left there in these studies by Helen. And then when they were going through this process of commercialization, which was almost like watching grass grow, it took forever. Initially, they were looking at using blue LED glasses, but there was this concern from, I guess, the lawyers that potentially this could increase risk because there was some of this talk about blue light hazard and more so blue light hazard on harming the eyes, which was interesting because I remember at the time, Leon Lack, he actually did his PhD on ophthalmology, not necessarily in sleep. And when he looked at the evidence for this, he said it wasn't really that convincing in terms of this blue light hazard. But nonetheless, the lawyers recommended, in order to reduce the risk, to move away from having these devices to be commercialized from blue light glasses to turning to green light glasses. And Leon's modeling a pair there. Finally, the retimers came out as green light glasses in 2012. And these are being fashioned by Celie Richardson, who did her PhD with me, basically looking at these LED glasses as a form of bright light therapy in the morning for teenagers and young adults undergoing bright light therapy for their delayed sleep phase disorder. And she compared these to a control condition, which was a placebo red condition. So we had an exact pair of these, although it was showing red light. And Cilly's results were actually quite interesting because, unlike Helen's results, there was no difference between the red and the green glasses. Both produced the same beneficial effects. So Cilly, she published her main findings, really showing that both colors would phase advance sleep timing, and you'd get all these improvements with sleep. Also showed that there were also another paper that there were improvements in insomnia symptoms, improvements in cognitive performance, especially in the morning, as well as improvement in depression symptoms, but from both types of glasses. But I guess something that's made me curious, especially over the last few years, is that what's been happening is that there's been many studies, many great studies that have been coming out. And really, they're inferring that blue light is harmful. And I think when I look at these studies, they're great studies, they've been performed well, so we should believe them. But there's this one niggling thing that has not allowed me to sort of fully absorb these. And I will get to this, what that is. But just to continue the story, after, well, around about the time when Celie was doing her PhD, or at least starting the PhD, I was doing some other work looking at technology use and sleep, and noticing that sort of circa 2011, there was a lot of people mentioning in their discussion sections that when it came to technology use and sleep, that probably one mechanism was that the light coming from these screens was enriched in blue light. And you can see this here in this particular study that I'll go through in a sec. But what we noticed is that at the time, around about 2011, there was only really one study that was, or a couple of studies that were looking at this concept of a bright blue screen that might be blue enriched and of affecting potentially sleep. One was done by Christian Kaioken from Basel, and certainly showing melatonin suppression and also showing that you'd have increased alertness. But funnily enough, that particular study didn't measure the effect on sleep. So this sort of opened the door for other researchers to do that. And that's what we did we started collecting the data in 2012 and published it in 2014. And so, as you can see here on the left-hand side, we had teenagers basically coming into the lab, and we subjected them to 3 different conditions. One was to have a bright iPad in their face for the classic hour before bed. And as you can see below there, the spectrogram basically shows this peak of blue that occurs when you've got a LED enriched screen. And around that time, there was also this app called F.Lux. You couldn't actually get it for an Apple device, so we had to jailbreak the Apple device in order to get it on there. This was before Apple invented their night shift mode. And then you can see with that one that you're getting basically this decrease of blue light, and therefore it's giving that orange glow. The other condition was having just basically a dim screen. So the screen was on completely dim, but no filtering. And to our surprise, well, even before I guess we collected the data, we tested the light coming from the screen. And coming from a background of having done bright light therapy, where you need sort of like intensities of light between a minimum of 500 to 1,000 lux, the maximum lux that we could get from this iPad was about 80 lux. And in order to do that, we had to basically sit on the bed with our knees up so we could bring the iPad closer to our face. And it's an actual uncomfortable position to be in for an hour to subject someone to 80 lux. So not only did I have doubts that potentially the light wasn't intense enough, but also I had doubts that people will actually do this in the real world. But nonetheless, when we went to test the amount of time it took for people to fall asleep or how much longer it took them to fall asleep in this study, it ended up being only a few minutes longer. And what's happened over the years is that that was actually the first study that really sort of tested the ability to extend sleep, or at least sleep onset latency, from having this blue enriched LED screen. And since then, there's been 10 other studies that have done this. And it's been very interesting seeing the translation of this to the community and to social media and so forth, because if you look at social media, there's been this rise from probably the late 2010s and certainly post-COVID, where a lot of people are claiming that the blue light from the screen is making it difficult to fall asleep. Whereas what's been happening in parallel is that data is not necessarily showing that. So last year we wanted to really highlight this, and we provided an updated model of how technology use can interact with sleep. And we went through different mechanisms in that review paper. And the first one was really looking at this bright light hypothesis. And we realized that as much as we can have a look at all of these different studies and we know that this is happening, we really needed to get the data from all of those studies and bring it together in one table. And this is the table here. So on the left-hand side, you basically, it's been ordered by chronology, so the year that it was published. But we were looking at objective measures of sleep. So we've got a combination, or different people use either polysomnography or they used actigraphy. There's been different settings. So people have either done this in the lab in controlled conditions like we did, or else they've done this in the home environment. They've done different manipulations. So we basically compared a fully bright screen compared to having an app that filters and reduces the blue. Other people have used blue blocking glasses. Other people have compared a printed book versus a screen. And these are studies that are done all around the world. And the experimental methods have been different. They've been either within subjects, so people are subjected to the same, or I should say different conditions, or you've had between subjects conditions where some people are subjected to one condition and a group subjected to another. But really on the right-hand side here is to sort of highlight what happens in all of these studies when you subject someone to a bright screen. In our particular study, it meant compared to a dim screen that it extended the time taken to fall asleep by 3.3 minutes. And then if you looked down that column, you've got the next study is minus 1.9. The third study, Chang and colleagues, that's actually probably one of the most popular studies, especially in terms of the translation of this topic to the community, that found an extension of 9.9 minutes. But really, if you look at that right-hand column and in your eyeball it and you average it, you're only talking about an extension of a few minutes by having a blue and rich screen in front of your face, which doesn't really marry with what is being said out there in the traditional and social media. And what's interesting psychologically is that when you are presenting people with this data and these studies, they don't necessarily digest it straight away. It's almost like people have a certain belief that screens are bad and blue light is bad. And what people will often do is that they'll critique that, which is fine. You know, that happens. And this is an example. Even Michael Herf, who invented F.Lux, was saying we shouldn't really focus on sleep latency. And other people are bringing up the Chang study compared to, our study and so forth, and talking about the fact that maybe sleep onset latency is not necessarily the best indication of this. I tend to disagree. I think if you want to look at what's going to create alertness, you want to have a look at how long it takes people to fall asleep. So I think the measure was actually quite fine. Nonetheless, it's always good to collect data to sort of see what is actually going on with the other metrics. And that's what we did in a follow-up commentary. So what we did here is that we looked at all of the studies that basically did not find an extension of great magnitude in sleep onset latency in studies that either looked at a bright screen or even looked at sort of stimulating content, like, say, for example, playing a violent video game versus watching a sort of relaxing TV episode. So we looked at all the other aspects of sleep. And if you collect all of these together, you find that still you're getting only a small change in sleep efficiency. You're getting an 8-minute difference in stage 2 sleep, And for total sleep duration, you're only getting a difference of 5 minutes. And that's not really much to write home about. So again, it seems to be that as long as people are basically using a screen, even if it's a blue and rich screen, in the hour or hours before bed, and they go to bed when they should, there's not this huge impact, at least that's what the data is saying, on sleep. Nonetheless, you still get these sorts of media stories, you'll get these sorts of social media posts where the title can be an accurate depiction of what probably a study is about. But in this particular case, the image might not necessarily reflect it. And I think this is what is happening in terms of this bleeding between scientific studies and then inferring that screens potentially can cause cancer. So again, it's got me still thinking about this question, is blue light harmful? I guess I've already demonstrated that I don't necessarily see that the blue and rich light from screens is harmful to sleep. But is it necessarily the case that blue light from artificial light sources, for example, is that harmful to our health? And to me, it sort of still doesn't make sense, and I'll run through why. So I'm a human sleep researcher. I do both experimental work and also clinical work. So I have been ignoring animal studies, but I thought I'd better have a look and see what it is saying. And if there are any animal people out there that know about this research, please share and let me know at the end sort of what you know about the effects of monochromatic and short wavelength light on these animals. But to summarize it, really, there are sort of some key elements here. One is that exposure to broad white, monochromatic green or blue light can lead to damage in photoreceptor cells. And I'm only going to say this once because I'm not very good with syllables, retinal pigment epithelium, so RPE, in rats. The photoreceptor cell death can occur from 2 hours after exposure to the light stimulus, and then several hours later, the RPE cells can die. And this is very consistent when you look at it across studies. In saying that, though, these studies are really looking at that research question of what happens when we're exposed to different sort of wavelengths of light and intensities of light and how that damages in sequence to the various parts of the retina. So there's a certain recipe with these particular studies that I'll just run through now. If you were to do one of these studies, you need to ensure that you have white nocturnal rodents. As soon as you use a pigmented rat, then suddenly you don't get this damage to the retina anywhere near as much as if someone, I should say, the rat is white. As soon as you use a diurnal rodent, one that is basically like us, awake during the day, they can actually withstand significant light to the eyes without damage as well. In order to get this damage, you also need to rear these rats in total darkness right up to the time from birth, right up to the time of the light stimulus. As soon as you start to produce what's called cyclic 24 hours of light and dark, say 12 hours of light, 12 hours of dark, that offers a level of protection as well. It is pretty clear that the short wavelength light, that's the one that's most damaging, so green and blues. What also happens is that these animals can be subjected to being injected with atropine, which basically dilates the pupil and keeps it dilated. Because what happens is as soon as you are subjected to bright light, and if it's short wavelength light, the body goes into a protective mechanisms and it actually constricts the amount of light coming in by constricting the pupils. The light exposure that these animals are subjected to range from something like 1200 lux to 6000 lux, much more than you would see from a screen. And the durations are somewhere between 2 hours of continuous light stimulus to 24 hours. So something far greater than what we sort of talk about when we talk about humans and the sort of exposure that they get to artificial light. But I'm going to just highlight one really interesting experiment in one of these studies because I think it gave a little bit of a hint about different wavelengths of light and the damage or the lack of damage that they can do. So I'll just sort of read from the top left here. After 1 week of exposure of cyclic 500 lux without pupil dilation, so basically these are animals that are subjected to 12 hours of light and then 12 hours of darkness for 1 week. And albino retinal cell loss was observed only in the superior retina exposed to blue LEDs. So basically, it was the blue LEDs that were providing some level of damage, and it was in the upper level of the retina. After 1 month of doing this cyclic exposure, both blue, green, and I should say, as well as white LEDs induced damage also in the inferior retina, the lower level. What was not said is that there was a fourth type of light that these animals were subjected to, which was not an LED, it was a fluorescent light, basically CFL. And after 1 month of exposure to this fluorescent light, this caused no retinal damage. So this got me thinking, okay, what's different about a fluorescent light compared to these LED lights? So what I've got here is basically a spectral distribution of a white LED, which is the purple or blue, depending upon your color perception, and a compact fluorescent light as well, which is the green. And so this is generated in ChatGPT. And really the only differences that can be seen here is that the white LED does produce more blue, and that's indicated here in this lower panel where you've got this sort of more intensity of blue around 450 nanometers. But there's also a little bump here of a slightly more red, which is a little bit reflected here in the top panel, the CFL, where you're getting a little bit more sort of the red color through here. So this got me thinking, is it possible that you have this sort of slightly more balance with a fluorescent light where you're getting a bit more red, and that's somehow counteracting or providing balance to the fact that there is a bit of blue there, whereas you don't necessarily see that so much with LEDs. So we've been talking about rats, and we might leave them for now and focus on humans and have a look at some of this human research when it comes to the sort of the combination of blues and reds. And really, what I want to do here is focus more broadly on health as opposed to sort of like circadian rhythms and sleep at this point. So this paper came out July of this year, and it was really, it might sound a bit bizarre, but what they were doing is that they were getting participants to come into a laboratory and they were shining light at their thorax for 15 minutes. And this light was non-visible red light, so near infrared light. It was at 850 nanometers, and the amount that was being projected was 9 milliwatts per centimeter squared. So these people were basically having this light shone on their back. They had almost like a head in a cardboard box, so it was all completely dark. But even the near infrared was sort of getting through into the box. So they even had participants wrapped with their eyes in alpha, so it couldn't get through. Then 24 hours later, they tested these participants. They came back to the lab and they basically tested their visual function with a color contrast. And when they were subjected with the near infrared light, 24 hours later, this group showed improvement in this particular type of visual performance task. So what this really suggests is if they're getting improvement because they're getting this near infrared light, that almost suggests that they were not getting enough near infrared light, and then they're creating this better balance that improves their vision. And I tried to search this paper to sort of see, were they getting insufficient near infrared light? Because as soon as you go outside, that's where you'll get near infrared light. So if they had this 24 hours distance between when they were subjected to this light and then, you know, some people weren't subjected to it, they had a sham and then they went home and then they came back and got tested, you would imagine they would have gone outside and essentially been exposed to this and might have confounded the results. But I contacted the senior author to basically ask, you know, what happened in terms of their amount of light exposure in that 24-hour period. And they didn't systematically measure it, but I guess the conclusion was that these individuals are primarily under LED lighting throughout their workday and when they go home, and they're not necessarily going outside so much. So again, it's almost like what's happening probably for these individuals is that we are becoming much more indoors. We are exposed to these blue and rich lights, LED lights and so forth, but we're not necessarily getting the natural outdoor light that has a lot more sort of red and near infrared in it. And as soon as you expose someone to that, then you start to see improvements, at least in this respect, with visual performance. So another thing that was quite interesting with this paper is on the lower left-hand panel here is what happens with light. Because with short wavelength light, when you're talking about blue light, for example, that will penetrate probably up to 1 millimeter into the skin. But what this showed, which was quite interesting, is that if you look at the lower left panel, this is pretty much the same type of clothing, which is a combination of a t-shirt, shirt, and a woolen jumper. And the human eye cannot see near infrared light, but the images basically show that compared to the left panels, which are basically taken from a normal camera, on the right-hand panel, when you have a near infrared camera that can pick this up, you can see that the light is shining through the chest area of that panel. So that's going through 6 layers of clothing, basically demonstrating that near infrared light can actually go deeper into the body, potentially. And that's what's shown here on the right-hand side, which was also in this paper. This is one of the authors actually having their hand over a near infrared light that's shining around about 850 nanometers. So all of those white areas is basically the light from that globe going completely through their hand. If you look carefully enough, there's no bone there that you can see. So it's going through bone as well. The black areas are where the light and the photons from that light are getting absorbed, and that's in the veins, basically the blood vessels that are going back to the heart. So potentially the mechanism that might be occurring here is that when the near infrared light, as much as it's not being provided to the individual's eyes, when it goes to another part of their body, it's then being circulated. The photons are basically proposed to be circulated and going to the areas of the body that basically need it, where they might be, say, deficient in near infrared light. At least that's the proposal here. So I want to run through some other examples that I actually find are quite interesting. This one here is done in Brazil, and it's looking at people that are in intensive care units in this particular hospital. And so many people have had experiences going into hospitals. You get a sort of sense of the lighting. It's not very good natural lighting. And people probably have the potential, even if they're in the hospital, to go outside at some points. But people in ICU, they don't. They're pretty much trapped in this environment. And what was interesting in this particular study is that they had 2 groups. One group basically had this device that was placed over them, like a blanket with LEDs, but it was a sham control. So these weren't necessarily switched on and weren't doing anything. The other group had the proper blanket of LEDs that provided both visible red light at 635 nanometers and near infrared light at 880 nanometers. And they had this blanket, basically, I think it was 90 seconds on different areas of the legs and the arms for a total of 15 minutes per day. And the actual result on the amount of time that these individuals stayed in the ICU was different significantly and meaningfully. In other words, the people that were subjected to this dose of red and near infrared light, they got out of the ICU, sounds like they escaped, 29% faster. So they spent 32 hours less time in ICU because they got better. So I find this one actually very interesting because this is much more in some ways controlled. These people were not going outside. They weren't necessarily exposed to red or near infrared light like you would usually get from going outside. And then when they're provided with it, then you're seeing this incredible health benefit there. And I tried to use ChatGPT to really find out what was this particular lighting that was in this particular hospital, because I found you can see that the hospital was the São Marcos Hospital in Brazil. And the only implication here, or the understanding, is that they're currently going through a revision of their indoor lighting as of the start of this year. And they're going to be bringing in more circadian friendly lighting and so forth. But what it means is that the lighting that they were under was really focused on what says in the lower right hand panel there is focused on visual comfort, performance, and safety. So you can sort of speculate or propose that potentially they were under LED lighting, maybe they were under sort of some fluorescent lighting, But the point is that they weren't exposed to artificial lighting that had sources of near infrared. So when you added that, then you see improvements in those particular patients. Moving on to another study, this is going back to that same group that were doing that visual performance one over in the UK. This is looking at glucose metabolism, and this is looking at two different conditions where you've got a placebo intervention, and in this case, you haven't got near infrared, but you've got visible red light at 670 nanometers. And these particular subjects were subjected to a glucose test. And what they found is that the maximum glucose spike from this test was lower by 7.5%, which is a little bit small, but still something. But overall, the elevation in glucose levels was 27% less when these individuals were subjected to this 670 nanometers of light for 15 minutes. So again, it's sort of going beyond vision, it's going beyond the ICU stuff and looking specifically experimentally at glucose metabolism, which can be the fundamental part, I guess, of a lot of metabolic disorders that a lot of people are claiming that, or really they're seeing the evidence that's linking potentially being exposed to light at night and these increased risk with metabolic disorders. And so on that note, you don't have to go far to find a study that will have a look at exposure to artificial light at night and its correlation or relationship with different forms of metabolic disorders. This particular study was done in 2023 in China. They were using satellite photometry and really associating that with a whole range of different metabolic issues, high blood pressure, obesity, high fasting blood glucose levels. And so the highlights and the findings from this study was that outdoor ALAN, so artificial light at night, was significantly associated with increased metabolic syndrome risk. And the people that were particularly vulnerable to this were males, elderly people, urban people, people living in urban areas as opposed to rural areas, and low activity populations as well. Now, clearly, I'm hiding something here, so time for the reveal. The rest of the title is saying, and the modifying effect of trees and grass cover. So as you can see in the right-hand panel here, there was a modifying effect between exposure to artificial light at night and these metabolic issues, with the third highlight here saying grass and tree cover partially ameliorated ALAN-related metabolic syndrome risk. And so when it came to really speculating as what the mechanism would be for why exposure to greenery areas would reduce the risk, the authors basically put forward grass cover and tree cover could reduce air pollution levels, promote physical activity, and improve mental health. And maybe that's the mechanism. And they have a citation for all of those. But one sort of mechanism or interpretation of the data was missed. And that is that greenery also reflects near infrared light. So this is an example I could find in the literature of the Siberian pine, a particular species. And on the right-hand side here, you've got basically a graph that shows just above 500 nanometers, which is green. That's where you'll see that trees are basically rejecting green. This is why we see leaves and trees as being green, because they're basically saying, no, we don't want you. And so we see that. But what we don't see is basically this near infrared light. This one here has a peak around about 720 nanometers. So potentially what could be happening is that when you see these studies looking at artificial light at night and this connection with some sort of harm to health, often what you will see is that people in urban areas are more at risk compared to people in rural areas. And that makes sense in terms of the fact that there'll be more artificial light sources in those built up areas. But what this particular study is saying is that you can still be in an urban area, and if you are around greenery, you've got less risk compared to those people still in an urban area that aren't exposed to so much greenery. And I think this has implications for even urban planning when it comes to different cities and being in that sort of situation where you can even do redevelopments and see if people can actually be exposed to more green spaces. So what could be the particular mechanism here? Well, it's this little fella called the mitochondrion. which is a very important part of our cells. So these are found in pretty much our cells of our body. My understanding is that they are highly concentrated in the eyes as well as the brain, for example. And if you have a look at these different studies that have been looking at the long red visible light as well as the near infrared light, they are all implicating that potentially it could be that the mitochondria are benefiting from this. And mitochondria are supposed to be, or they're termed these days as the battery of our cells. So they basically produce energy. They go through these different steps and then they produce something called ATP that I'm not going to pronounce because there's way too many syllables. And that ATP gives the cell energy and therefore us energy. So they're sort of thinking here that there may not be enough exposure for people. They're not going outdoors so much. They're not necessarily having their mitochondria having these sort of health benefits. But when you do expose them to natural near infrared light, or if you get it from artificial sources from photobiomodulation, so many syllables, that's when you'll start to see that potentially you're getting the benefits, and it might be because it's helping the mitochondria. Conversely, again, back to the UK and with the same group, looking at blue light, this study was done in Drosophila, so flies, and they found that mitochondria can actually be somewhat impaired by blue light. So in this particular study, they were looking at exposure to blue light for 15 minutes per day within a 12-hour light cycle for 1 week for these flies. And they found that there would be a real peak sensitivity at around about 420 nanometers. So on the right-hand side here, you've got these different graphs. And looking at graphs A, B, C, and D, they're called complex 1, 2, 3, and 4. Now they're representing sort of like these 4 sequential stages that basically sum up what's called the electron transport chain. So as electrons are flowing through the mitochondria, and they go through those 4 different stages to then produce the 5th stage, which is ATP, which is graph E here. Now, with complexes 1 through to 4, there's a significant difference between exposure to this 420 nanometer blue light compared to darkness. However, when you get to the final important part, which is the production of ATP, there wasn't a significant decrease, but it is still trending in a downward direction. And one would imagine if this is supposed to be our battery, then what happens in terms of the whole mechanism, the whole, individual, so to speak. And here, looking at part F, you can see in terms of locomotor function, like performance of these flies, you're not necessarily seeing an impairment there. But nonetheless, there's emerging evidence to almost sort of say that there is, this potential for blue light to create this harm to mitochondria, but we're not necessarily seeing that in the final sort of product in terms of energy production and performance. Now, I can imagine that there's, and already this is already happening, at least on social media, that people are sort of talking about how blue light can be harmful to your mitochondria, get off your screens and so forth. But if you're careful enough and you actually have a look at the output from screens and you look at the nanometers, now 420 nanometers is a very specific area where mitochondria can be affected. If you look at the spectral distributions of various light sources, so we've got the iPhone 10 here, a desktop monitor, and a white LED, you're basically seeing that there's not much 420 nanometer light coming from these light sources. Even from a fluorescent tube, you're not getting much at all. In contrast, people are always talking about the blue light that's coming from screens being above 450 to 480 nanometers. And if you actually look on the graph here, in terms of the impairment to the mitochondria at around about 450 or more, you're not really getting much impairment or effect whatsoever. So once again, we can't necessarily translate studies like this to sort of say that screens are going to affect mitochondria and then cause all of these metabolic disorders. And this now brings me to why I have been resistant to really adopting a lot of the studies that are talking about the harms of blue light, because inevitably, as much as these studies are great, they're well designed, they are aligning and showing that there are these impairments or this harm. I cannot I cannot get past the fact that the most light that people are subjected to in terms of blue light is as soon as you step outside. Is far greater than any artificial light source. And this is an example here. If you look at your 24-hour day, the greatest amount of 420 nanometer light you should be exposed to is as soon as you step outside. Even the 450, 480 nanometers that you get from screens, you get far more blue light stepping outside. So it should stand to reason that going outside should kill us. I mean, it probably does in Australia. You've got to be careful, a lot of animals and stuff like that can get you. But then potentially, what's going on here? Is it the fact that we're also exposed to the greatest amount of red light and near infrared light that might be balancing out the blues here? And so I think we probably at this, at least I'm at this point where I think I'm standing back and looking at the forest and thinking that the circadian field has been really focusing, and we've sort of anchored our viewpoint on looking at blue light. We've found some really interesting discoveries back circa 2000, give or take, but that has not allowed us to sort of look more broadly at the other elements of light. And there's been a lot of conclusions about how the blue enriched light from artificial light sources can cause harm. And I don't necessarily agree with this translation and this messaging. And I think this is one example that I feel compelled to point out. This was just mentioned back in September, so just almost over a month ago. And again, it's an approach that uses what you would call fear mongering. And fear can be a message that can change people's behavior, but there's other ways you can change people's behavior. But I think this is a classic example where it is basically a laundry list of all of the harms that have been shown to be correlated with blue light. So obesity, diabetes, immune disorders, heart disease, psychiatric disorders such as anxiety, depression, breast, prostate, and colorectal cancers. Now, I don't like this. I don't like this sort of way of telling people how they can sort of change their behaviors in order to improve their health, because a lot of this data really comes from studies that look at the most severe exposures to basically artificial light at night, which are shift workers. And if you think about a night shift worker, these folks, they don't necessarily get to change their behavior, especially in this economic climate. And I don't believe that fear mongering is an approach. They can't necessarily change their jobs. And so if you look at some of the classic studies, this one was a fantastic one that was done in 2024. And if you look at the graphs, certainly exposure to artificial light at night, somewhere between after midnight to 6 a.m. in terms of all-cause mortality, that is quite bad. Especially this here is if you are basically at the 90th to 100th percentile in terms of your exposure to artificial light at night. And conversely, if you are at the sort of 90 to 100th percentile during the day, not getting exposed to sort of natural light, that's also going to be not so good for you. And if you look at the percentages of the potential people in this category, that does align with the amount of people that frequently would have night shift. And if you're doing night shift, what are you going to do? You're going to be basically sleeping during the day. So you're possibly not getting exposure to potentially healthy natural light that would contain near infrared light that could potentially counterbalance this exposure to artificial light at night that might have the blues in them. So to sum up, I think what happens, at least when if any of you guys are doing clinical psychology, the idea is that you're trying to understand the problem. You're trying to conceptualize it and think, what is the underlying problem here? What is the contributing factor? Once you identify that, then you match that with some sort of solution. So I think what the circadian field has done is really to identify the problem as blue and rich lights are harmful. If you have that approach, that means, or it leads you to the solution being to reduce blue light. And so what are the solutions for that? They include blue light blocking glasses, blue light reducing apps, blue depleted light globes, no LED screens at all, no overhead lights, but that would also technically mean no shift work. Because again, if you look at the data at who's the most vulnerable, who shows the most impact on their health with blue and rich lighting, it is night shift workers. And we can't necessarily ask them to change their shift work, their work at all. And I really do feel for these guys because it's almost like we have the privilege of sleeping during the night with feeling quite comfortable that these guys are there if we need them. If we get ill, we go to a hospital. If we need the police, if we have the firefighters, they're all there and available for us. So I think the messaging has to be quite different. And I think the evidence now is suggesting it should be different. If we reframe the problem as the fact that the depletion of exposure to near infrared light is harmful. That's the problem. What that means is that the solution should be that we increase exposure to near infrared. Therefore, the solutions would be pretty much to go outside, get natural light where possible, especially in green spaces. In the absence of that, if you can't get outside, as it was demonstrated with the ICU study, and even when I think about, my 99-year-old nonna, my grandmother, who's in a nursing home, she's always indoors under these artificial lights. And as much as you might get next to a window, windows are basically designed to basically reflect, not allow the passing through of near infrared light because it creates heat. So they're trying to basically control that. So in those instances, that's when you probably do need some sort of artificial light source, and you do have those options of photobiomodulation. Furthermore, really, we've gone from a place where we've had these incandescent lights, and incandescent lights actually have been a form of warm, heated light globes that do produce a lot of near infrared light. Since we've switched to LEDs, we've lost that. And I think no matter which side of the fence that you're on in terms of this argument, we all agree that the indoor lighting needs to change, and we need to bring back essentially indoor lighting that basically increases the amount of exposure to near infrared light. So I think that we have to really sort of think about the messaging, and that can help change the behavior. We can't necessarily ask people to change their jobs if they're a night shift worker. We can say, try to get 15 minutes of natural light before you sleep or after you sleep. So that's more of a positive message, and potentially that might actually be the solution as well. So thanks for that and for your attention. And it's been a bit of an eye-opener for me. Sorry about the pun, but I'm happy to take any questions. So thanks.